Welcome to the Explainer. Today we're doing something really cool. We are prying open a mathematical black box. We're going to figure out exactly how algorithms actually measure forecastability and complexity in our data. Because, if you've ever stared at a massive, messy data set and wondered, is there actually a predictable pattern hidden in here, or is this just pure, unadulterated chaos? Well, you are in exactly the right place. Okay, let's dive into this. Here is our roadmap for the journey. First, we'll meet permutation entropy. Second, the Bandt-Pompey pipeline. Third, counting and Shannon entropy. Fourth, normalizing the score. And finally, some big picture takeaways.
Part 1. Let's officially meet permutation entropy.
Look, anyone who works with raw data knows it can be incredibly messy, right? You've got sudden spikes, random dips, bizarre outliers that make your chart look like a toddler just went to town on it with a crayon. Figuring out if a signal is actually predictable underneath all of that noise is a massive headache. Enter the Bandt-Pompey procedure. This is our elegant solution for cutting right through that noise. It's a frankly brilliant method used to calculate permutation entropy by converting sequential data into what we call ordinal patterns. That is what allows us to accurately measure a signal's complexity. And don't worry, we're going to dissect exactly how it does this, one logical step at a time. To do that, we've got a neat 5-step pipeline. Think of this as our progress bar for the explainer. We've got embed, rank, count, entropy, and normalize. We're going to take raw, messy data at step 1, and we're going to output a beautifully clean, totally interpretable score at step 5. So let's get into it.
Part 2. The Bandt-Pompey pipeline. Now, to really build our intuition here, we aren't going to jump straight into some massive, complicated, real-world data set. No way. Instead, we're going to use a highly simplified 7-point toy series. By limiting ourselves to just 7 carefully chosen values, we guarantee that we can easily track the patterns by eye. It lets us watch exactly how the math works under the hood at every single stage of this pipeline, without getting lost in the weeds.
Step 1 of the pipeline is what we call embed. Imagine taking a small frame, like a little viewing window, and sliding it across our data one single step at a time so we can capture its temporal evolution. For this, we're using a window size, or to use the fancy math term, an embedding dimension of 3 and a delay of 1. So by sliding this 3-point window along our 7-point series, we generate exactly 5 distinct overlapping windows. That leaves us with a neat 5-row matrix of localized data chunks to work with. Now for step 2, rank. Now, what's really interesting here is a mathematical operation known as a double arg sort that transforms our raw data. But honestly, let's ditch the jargon and just put that into plain English. If our raw window captures the values 4, 7, and 9, the procedure simply ranks them from smallest to largest. 4 is the smallest, so it gets a rank of 0. 7 is next in line, getting a rank of 1. And 9 is the largest, getting a rank of 2. So 4, 7, 9 literally just becomes 0, 1, 2. The algorithm completely stops caring about the actual underlying numbers. It only cares about the relative shape of the pattern. And that leads us to this phenomenal quote right from the source material. From here on, the actual values are irrelevant. Only their order survives. I mean, this is the absolute core aha moment of the entire Bandt-Pompey procedure. Because the algorithm only looks at the rank, it becomes entirely immune to wild outliers or monotone transformations that would instantly break traditional forecasting metrics. A subtle little bump and a massive mountain? Treated exactly the same. One wild billionaire walking into a room doesn't ruin your average income math anymore, because to this algorithm, a spike is just a shape.
Part 3. Counting and Shannon entropy.
So we've transformed our messy data into clean shapes. The next logical question is, how many possible pattern combinations are we actually dealing with? Well, because we chose a window size of 3, the math dictates there are exactly 6 possible ordinal patterns. That's literally just 3 factorial. You have 3 options for the first spot, times 2 options for the second spot, times 1 for the last. So in any given window of 3 data points, there are only 6 possible ways those values can ever be ordered, period. But let's look at what actually showed up in our specific toy series. Across those 5 sliding windows we made, we only actually found 4 out of the 6 possible distinct patterns. Some ascending or descending shapes showed up a couple of times, and some didn't appear at all. This is the count step of our pipeline. It gives us the raw relative frequencies we need to power the actual complexity calculation. Next up is the entropy step.
We take those observed relative frequencies and plug them straight into the Shannon entropy formula. Borrowed directly from information theory, this formula essentially measures the element of surprise. And crucially, only the patterns we actually observed contribute to this math. If a pattern didn't show up in our data at all, it gets totally ignored. It doesn't skew the results. By running this calculation, we get a raw mathematical score that reflects how predictable or how surprisingly chaotic the sequence of those shapes actually was.
Part 4. Normalizing the score.
Now, a raw mathematical score floating out in the void isn't always super easy to interpret, right? So we need to normalize it. This is the final step in the pipeline. To do that, we have to find our mathematical ceiling. We calculate the log base 2 of our maximum possible number of patterns, which, if you remember, was 6. The log base 2 of 6 gives us approximately 2.585. Think of this number as the absolute maximum entropy we could theoretically ever see when using a window size of 3. And this brilliantly illustrates why we do that. By dividing our raw entropy score by that ceiling of 2.585, we neatly squish our final results onto a beautiful, simple scale from 0 to 1. A score of 0 means perfect order, like only one single pattern showed up every single time, meaning the data is entirely predictable. On the flip side, a score of 1, that means total chaos. Every single pattern was equally probable. That basically leaves us with the mathematical equivalent of static on an old television set. Pure white noise. Part 5, Big Picture Takeaways. All right, we made it through the pipeline, but let's zoom out. What's the actual practical value of mapping everything out like this? Well, first, you really need enough data. Remember our toy series only caught 4 out of 6 patterns? To saturate the pattern space and get truly trustworthy values, your total data points need to be way, way higher than your possible patterns. Second, this entire process is incredibly computationally cheap. I mean, it's literally just counting and running one simple formula. That is huge because it means you can easily scale this to screen millions of time series for forecastability at absolute lightning speed. Finally, while it is incredibly powerful, it's naturally blind to things like amplitude or slow, lingering structures. But that is exactly why variants like weighted permutation entropy or multiscale permutation entropy exist, to jump in and catch those specific complex nuances. So the crucial point here is that measuring chaos doesn't have to be some intimidating mathematical black box. We literally just took messy raw data, converted it into robust ordinal patterns, and popped out a pristine 0 to 1 score of predictability. Which leaves me wondering, if you dropped your own dataset into the BAMP-POMPI pipeline right now, would it reveal some hidden predictability you didn't know was there? Or would it just be perfect chaotic white noise?